I like this. I like the cool. Thick. Okay. Now, I'm going to take this very slow because a lot of the times this topic is approached in a very mechanical way. That's how I was taught complex numbers for the first time when I learned it when I was in school. I was just given the format. I know that you all have. Now, just tell me, you all have already learned this topic by now, right? Am I right? Right?
Yes.
Yes. Okay. So the way it was taught to me was by giving the, I think even in the textbook, but that's a better approach. Was just giving by giving the that format. A number in this form is a complex number. That's how it was introduced. That's all. And then the details of it were revealed, but the initial, the first expression matters. So I have a different approach when I teach complex numbers. Okay, so I know that you all of you know that a complex number is a number in the form a plus bi, where a is the real part, b is like, that's just that doesn't give you the it doesn't show you the beauty of complex numbers. So what I want you to think of this first. Okay, now don't write anything until I say write. Don't write. I'm just writing things to explain things to you. If you look back into all of the mathematics that you have learned in your school life from the primary grades, the first thing that you learned, maybe in grade 1 or kindergarten, you learned numbers. You learned counting numbers, 1, 2, 3, 4, and you count on your fingers. So your mathematics learning started with the simple, if I call it a topic, numbers, right? That was when you were in primary grades. You started to learn about numbers. Then maybe in grade 4, 5, you were introduced to 3, 4, 5. You were introduced to, so numbers in the sense counting numbers. You learn 1, 2, 3, and all that, right? 1, 2, 3, 4. You learned how to count. In grade 1, 1 to 10. In grade 2, 1 to 20. In grade 3, 1 to 100, and so on. You just expanded the how far you can count. And then came fractions, I'm sure. Later on, you learned fractions. So, and then you learned that fractions are also numbers. So they are all numbers, like half and quarter and things like that. And then when you were in middle school, 6, 7, you were introduced algebra. So this we called arithmetic, right? Anything to do with numbers. When you are learning everything to do with numbers, how to operate with numbers, all that belongs to what we call as arithmetic. And then, so that was in the primary grades. And then in the middle school, grade 6, 7, you started learning about algebra, how to work with a general expression where you have a quantity. You learn how to work with a quantity that you didn't know the value of, for sure. So you learn to take it as by using a letter like X. So that was algebra. And then you came to solving equations and how to manipulate these expressions, factorizing, expanding brackets, all those things. And then when you came to like O levels, there were topics like trigonometry, and then graphs and little bit of matrices. I'm just showing you all different kinds of little topics that you touched down the line. Like I'm coming in an order. It's like a timeline. And then, so like this is primary. This is like middle school, grade 6, 7. And this is like O level. right? And then when you came to advanced level, you started learning calculus, differentiation, integration, calculus, right? Calculus, and then all these very sophisticated topics, out of which I think calculus is the biggest one. So I will just write that. And then more of trig, more algebra, the advanced algebra, all that came in advanced level. And now here we are at the end of your school life, at the end of your, in your mathematics module P3, the last topic, it's like, that's it, right? And then you'll be finishing school and you'll be going into whatever the field that you're going to go in. And in this last moment, what we are going to learn now, I want you to have a feel of the path that we came along, starting with the most simple concept, numbers, and then ending with like calculus. And then this last, the grand finale, the last topic. For the last topic, what you're going to be doing actually is you're going to go back to numbers, which is like, then you should ask now, if I talk to you, assuming that you have not yet learned complex numbers, if I say that we are going back to numbers and we are going to learn numbers again, you would say, what more is there to learn? We know everything about numbers. But see, we are going back to that beginning because the picture is not yet complete. Even though we came so far, we have done what we have done without a complete understanding of numbers. And that just has to blow your mind, because with the knowledge of numbers that we had, we could come up to calculus. But then now I'm saying, sorry, you learned numbers, but that was not a complete lesson that you learned in your primary grades. So we have to go back there and complete that picture. Okay, so it's that's what we are going to do. So we are going back to it's like going back to primary grades. So let's talk about numbers. And now don't write anything. Let's think about numbers. The first thing I want you to put into your heads is that, because if we don't think about this consciously, we take it for granted. I want you to be aware of, and then be mindful about, and remind yourselves that numbers is something that we made up, human beings made up. It was not, there was like, it's so natural to us now. It's like there, like it's there. It's not there. We made all this up. 1, 2, 3, we made it up. Where is 1? Can you show me 1? Can you show me 2? Look around you and show me number 2. What do you mean by number 2? It's just something that we made up because we had a need to do that in the early times. Now, who first came up with this? This is the first type of numbers that we created. This is a creation. I think it's not there. We created it, and now it feels like it's there. The first type of numbers that we created were counting numbers. And why we did that, I want you to remember, and I want you to understand that every type of number that you know now were created by us when there was a need. You have a need, we need some kind of numbers to measure this, or to do this, or to fit here. Let's create it. That's how it happened. That's how it all happened. The first type of numbers, which are counting numbers, or what you call as natural numbers, were created too in the what time you call it, Endera Yuga. I don't know how to say it in English. Like the battle Endera Yuga, is it called? What do you call it? Like when they have they had herds of sheep. Is that how you say it? Like they were depending on animals like chickens and sheep and all these. I'm talking about a very ancient times. They needed a way. Now, this is when they had no numbers. Just imagine a world when you don't have that vocabulary. You don't know 1, 2, 3. There is no 1, 2, 3. people needed a way to keep track of how many sheep they had in their herd of sheep. So when they took the herd, is that what you call them? Herd of sheep? When they took them out, herd of sheep, right? And in the evening, when they brought them back, they had to know whether all the sheep were there. So initially, what they did was they used their fingers. It all started with fingers, because it's amazing that our body, the way it is built, we have a way. This is our best calculator that we have, our fingers and the toes, and this is why our number system is based on 10. If you never thought about it, because we have 10 fingers, that's why it's based on 10. That's why people start to group numbers in 10, and it's not a binary system. I hope you know what I'm talking about when I say it's a system based on 10. That's why we have only 10 numerals. All numbers can be written just by using 10 symbols, 0 to 9, right? That came from with this. So the way they kept track of how many sheep they had was they made a one-to-one mapping. Okay, this is that one, that is. So they use their fingers to match. If there were 10 sheep, they would map one by one. This is that one, this is that one, like that. So the need was there for some mechanism. We need something to so this count to see how many, for the question, how many do I have? How many sheep do I have? I need something. That's when they created 1, 2, 3. And that's why it ended up being a 10-based system, because you have 10 fingers. So this 1, 2, 3 came in. Now, I want you to be in this timeline. I'm like going along a timeline. So this was when only counting numbers were there. Now, before that, no numbers. Now you have counting numbers, nothing else. Just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Count. You have counting numbers, because that's all you need. You don't need anything. Until a need arises, you wouldn't create something, right? And then later, they wanted, when they had to talk about a part of something, like they break something into 2. So you first have a 1, and then you need pieces of it. How do you call those pieces? So I will just quickly go through this. So then came fractions, and then a notation for fractions. And you should think, why do we write fractions this way? A fraction is written by using 2 numbers. And that's very, for small kids, if you can remember the first time you learned fractions, it's 1 over 2, 2/3. When you write a fraction, there are already 2 numbers in it. 2 is there, 3 is there. That doesn't mean you have 2 things or 3 things. But with the use of 2 numbers, you are expressing what part of one whole you have. So that's the notation. And then came fractions. So with this, this is like the timeline I'm writing. This is the time. Now we are in 2021. I will also build the most familiar way to us for visualizing numbers, which is on a line. We all are familiar with visualizing numbers being on a line. So if I use that model to represent to you how this model, the number line, would have looked like when we only had counting numbers. If the only numbers you had were counting numbers, you wouldn't have had a line. You would just have had, okay, I have 1, I have 2. You would have just had a bunch of dots, right? There is no line. And then you have 3, and you have 4, and so on, 5, and so on, right? And then just imagine how this, but now we have a whole line. Let's just think of it as, we are just trying to see how this line got filled up with the creation of each new type of numbers. So when the fractions came, half is right here. Okay, now this is going to get filled. Half is here, and the 1/4 is here, 3/4 is here, 1/3 is somewhere, 1/3 is somewhere here. And then you can see that with all the different kinds of fractions, the middle of the in between of these counting numbers is going to get filled. So a lot of dots here, each dot representing a fraction. So all that came in, right? So So 3.5, 4 and 2, like that. So now it's getting filled. And then sometime later came 0. We didn't have 0 in the beginning, right? And it took a very long time for people to accept 0 as a number. Now for you, it's no big deal. If you, I don't know, do you remember the first time that you learned 0? When I don't remember. I don't remember. I wish I remembered. So for me to think, how did I feel about it? Because I don't remember. Because for the human race, it took decades and I think hundreds of years. They first used 0 just as a placeholder to write a number, like when you wanted to write 203. So in the hundreds place 2, in the ones place 3, just to say there is nothing in the tens place, they used let's use the circle just to say there is nothing there. So 0 was the symbol 0 was used just as a placeholder, because you can't leave a space there. It's confusing. Let's draw a 0 to say that there is nothing, but it was not accepted as a number. But then later, oh, it's a number, it's right here. If 1 is here, 0 is here. So it was accepted as a number. So 0 came into your number system, right? So all the fractions are there. Oh, this is not half, this is half. Now, why didn't anyone? This is 1.5. Did anyone not think about it when I was drawing it? So actually so 0 came into that. No, okay, right. So anyway, so 0 came in. So for a very long time, this was your number system, and this was your line. That was your line. And for the longest time, so algebra was getting developed in the history of time. And when people were solving equations, when they came to solving equations such as, for example, like this, x plus 5 is equal to 3. Suppose you come to this step, like you're solving an equation and you finally come to this step. And in the next step, you would have to do x is equal to 3 take away 5. And people used to say, there was a time that when people said, there is no solution here. Why? What is look at your number system. It starts from 0, 1, 2, 3. 3 take away 5, you can't take away 5 from 3. So there is no solution. Is this familiar, saying so, no solution? Do we not say no solution now for certain equations? So now we have an answer for this now, but there was a time when people said no solution for that because they did not have a number to represent 3 take away 5 until they started creating. Somebody said, why not? No, let's say, let's create it, right? So then came negative numbers. So somebody said, if I have, so 3 is here. If I take away 1 from 3, I go back 1. So I get 2. If I take away 2 from 3, I go back here. I take away 2 and I end up at 1. 3 take away 3, that is okay, I can do that. 3 take away 3, I go back here. 3 take away 4, where to go? You fall off of there is nothing to, but then somebody was brave enough to say, hey, wait, and the thing was, it didn't violate the rest of the mathematics. It was rather creating a more complete picture of it. Why not? Hey, let's say, what could be before 0? So this whole negative concept, the opposite of these numbers, additive inverse, we call it -1. Let's call it -1. But do you see a -1 around you? Like, what do you mean by -1? You have to be asking that question. But now again, that took another so many of years for people to accept. So this line that we had starting from 0 suddenly started to have, it was suddenly an infinitely long line, where 0 is kind of in the middle. There is no middle in this line because it's an infinitely long line, but there was some kind of a symmetry around 0. And all these negative numbers were created. And with that, all the negative fractions and the complete replica, is that what you call it? was created on the other side of the line, but they were all negative, opposite numbers. So that was done for, why did people do that? To as a because we needed that. We needed a way to talk about 3 take away 5, and then they created it. That let's call these numbers -2. But I want you to like feel that feeling. If you were in the times of when this was happening, you would, even if you had no clue of negative numbers, like it was not created yet, then it would make complete sense to you why we say, yeah, of course, there is no solution for 3 take away 5. There is no such number here, right? So now your number line, after negative numbers were created, why is this blinking? Do you hear me? See me and hear me well?
Yes, miss.
My thumbnail is like, I don't know what's happening. Okay. Now here's your number line now. So you have 0, you have 1, 2, 3, you have -1, 2, 3, all of them infinitely long. You have the fractions going on in between all of these. And then again, for another so many years, people thought, now even you should feel this. Now look at this. When I fill these in between spaces with the dots saying that these are all fractions, just think about how many fractions you can have between just 2 adjacent counting numbers, like between say 1 and 2, or let's take 0 and 1. It's easy to think. Let me zoom this, and like if I zoom this 0 and 1, you have half. Just think of, now I will not zoom the paper. I will just redraw it. Like if I just draw this part, I zoom it. This is 0, this is 1. Just think about how many numbers I could fit in between 0 and 1, how many fractions I could fit in. So you would then understand, it's like I can see how all these little spaces, how they get filled by a dot representing a number. Because think about it, you have even 2 over, like if I go in order, like you have half, you have thirds, you have quarters, you have fifths, you have sixths, you have sevens, you have eights, you have nines. Is there an ending to this? You have tens, you have 11s, you have 12s, and you have hundreds, and you have thousands, you have millions. Do you see that there is no end to this? So all those numbers have to fit in between 0 and 1. So you will see that that's how this line gets filled. So there are no spaces between 2. Like if I show you that there is a number here, there is a number immediately after that, the dot immediately after that. And between those 2 dots, there would be yet another infinitely many fractions. I'm going to take you to the concept of irrational numbers. Now you already have learned this, but before irrational numbers came in, people thought that the number line was filled just with fractions, just with, these are rational numbers, right? I just wrote unit fractions, but if you take fifths, there are 4 of them, like 5 of them. 1/5, 2/5, 3/5, 4/5, 4 of them. And when you say 1/5, that's you're here. So for each of these unit fractions, there are like the pieces that you can get out of it, right? When you have thousands, there is 1,000, 2,000, 3,000, and so on. So all of these are here. But then, so we thought it's filled, but then somebody came in and said, with the discovery of √2, again, now how did that happen? When you draw a square that is 1 by 1, the diagonal of that square, should have, from Pythagoras theorem, should be square root of 2. So, but they were trying to find square root of 2. So what is square root of 2? Is it what fraction is it? How do I write it as a fraction? And they could see that if you can't write it as a fraction. I don't know whether you realize what this means. What do you mean by you can't write it as a fraction? This number is between 1 and 2. No, it's between 1 and 2, right? 1 and 2, somewhere. It is somewhere there, but it's not a fraction. What does that tell you? It's not a root 2 is not a fraction means I thought that with fractions, this was all filled, but no, there had been empty places, empty spots on this line that was not filled with fractions. Do you understand that? And then to see there are more of these numbers on this line than fractions. When I say fractions, fractions means rational numbers. A rational number is a number that can be written as a fraction with two integers. The line that we thought was completely filled with just fractions turns out to be actually very empty. It is mostly filled with these type of numbers, irrational numbers. Anyway, so irrational numbers came in. Now this number line is completely filled. When we just had fractions, before we had irrational numbers, we thought it was filled with just fractions, but it was not. It was mostly empty. And then that emptiness was filled with irrational numbers. Now no one else could take a place on this number line. It's all full with the numbers that we know now. So this is what we call the real number line. So when you say real numbers, it's all of these numbers, the natural numbers, 1, 2, 3, whole numbers, 0, 1, 2, 3, negative numbers, -1, -2, -3, integers, that is all the negative and positive whole numbers, and then fractions, and then irrationals. All of that make up your real number line. So any point on this line is one of those numbers that I mentioned, and any of that number that I mentioned is sitting on this line, and this line is full. There are no empty spots anymore, right? So these are all real numbers. And then again, when people were solving equations, we stumbled upon equations like this. Say x squared plus 1 equals 0, and then say you're solving an equation and you come to this step. So you would go x squared equals -1, and then you square root it, then square root of -1. No solution. This is absurd. There is no solution. There is no square root for -1. Why did we say that? Because we don't have that number on this line. Why do we say that? Because so if you want to think of square root of -1, you have to show me a number that when multiplied by itself gives -1. I'm sorry. Gives -1, right? This number would be, this number would be what's negative square root, right? Square root of -1. If there was a number, square root of -1, that when I multiply that by itself, I have to get -1. -1 is right here. Now let's try to find where this number is. Where this number is negative. Square root of -1, is it on this line? Can I find who is negative? Who is square root of -1? So 1 times 1 times 1 is 1. So it's not 1. -1 times -1 is also 1. So it's not -1. So then there is no number that when multiplied by itself would give me -1. So this was, right? So it makes sense. There is no solution, and this doesn't exist. We would say doesn't exist. Such a number does not exist. It didn't exist until someone was brave enough to say, let's try to create that number so that it doesn't violate the system of numbers that we have built so far, and it is consistent with all the knowledge that we have in mathematics. it is consistent with, operations like addition, subtraction, and multiplication and division, that if it doesn't disturb our system, just like how we created negative numbers, it nicely matched everything else. And there were applications of it. That's the other thing. Now, negative numbers by itself, we might think there is no use. What's the use of that? No, it is useful. It is used to say something. For example, we have things below zero, like the depth, height, or temperatures. There are things that could match to that, right? So now they wanted to fit this in to this picture. But something that we know for sure is this number is not on this line. And now I want you to take a moment and just think about that. What do I mean when I say that this number is not on this line? That's why we say it is not, so it doesn't exist. There is no such number in our number system, not on the real number line. Do you all see that? Because I can't find a number that is on the number line that when multiplied by itself could give -1. Are you with me?
Yes.
Don't fall asleep.
Nope, I'm still here.
You're still here, no? Is everyone here? Okay, yes. Oh, have you been dropping messages? I'm just seeing your... Oh, I'm sorry. I'm just seeing all your messages now. God brought that number. Which number God brought? Malit. Okay. So before I show you how fascinating the way they brought in this, you were thinking about root of -1. Let us revisit. Now, I would tell you now, this whole intro is going to take a long time, but it's worth it, okay? Because I want you to have one day, even some of you might not do a lot of math in your future studies. I don't know. Even if you do, you would get into a very mechanical form of studying of math when you go to university. So I wanted to, even if you don't do any math hereafter, what I want you to have with you is this big picture that I'm trying to give you. You might forget the details, but you will remember maybe the fascination of math. Okay. Yeah. So I'm trying to give some message out of this. That's why. Okay. So I wanted to think of, because this is trying to think of the square root of -1 has to do with the operation multiplication. So because we have to think of a number multiplied by the same number has to give -1. So I'm going to really think about what multiplication means. So actually, now you and I, we have not thought of multiplication in this way that I'm going to show you now. But I'm going to show you a way in which we can think about multiplication. Multiplication can be thought of as a rotation of a number, as a rotation. Okay, here's how it works. When you are multiplying two numbers, say if you are doing 2 times 3, okay, actually what we are doing is any multiplication starts with 1. You might be, to multiply, you need at least 2 numbers now or more. The minimum the number of numbers you need to have are 2. You need 2 numbers to multiply. But any multiplication, you have to think as starting off with 1. You start with 1 times 2 times 3. Any harm? No harm, right? Because when you multiply by 1, that doesn't change anything. So any multiplication of 2 numbers, here onwards, you think of it as first starting with a 1 and then times, and this is how it is. This is how it happens, okay? So you have your number line. Here's 0. Say 1, 2, 3, 4, 5, 6, 7. any multiplication, you start with 1. And I want you to think of any number. So when I say 1, think of 1 as a little arrow from 0 to that number. So that's 1 unit long. It represents 1. It's like a vector. Okay, vector in 1 dimension. So you can have directed line segments on this real number line. It's numbers on a line. It's vectors on just a one line. So when I say 1, you think of the arrow starting from 0, the position vector of 1. Okay, so starting from 0. If I say 2, 0 to 2, that arrow. So when I want to do 2 times 3, you start, what happens in this operation is this. You have the 1 vector, okay? Now remember, we have positive numbers and negative numbers. So far, that's what we have. We have positive numbers and negative numbers. So 2 times 3 means they're both positive. If you're multiplying by a positive number, if your number is positive, so you start with 1. If your number is positive, multiplying by a positive number, think of it as, because it doesn't change anything, your direction, you can think of it as rotating 360 degrees. It's like rotating, I mean, that means you haven't turned at all. If you turn 360, it's equivalent to having not turned at all. But you can think of it as rotating 360 or 0. Multiplying by a negative number is rotating by how much? Because if you rotate 360, you end up right where you are. Oh, I didn't mean to have a oval. Multiplying by a negative number is rotating on this plane, or you're rotating on this plane. Okay, I didn't tell you that. Your arrow is rotating on the plane. Multiplying by a negative number is rotating by 180 degrees. So then you're changing the direction. That's why it's a direction change. If positive is going left, negative is going right. You've rotated 180 degrees. If positive is up, negative is down. Because see, the sign change is rotating you by 180 degrees, right? So if I'm doing 2 times 3, that means I start with 1 and multiply that by 2 means it's a scaling. It's a scaling. I go in the same direction 2, and then 2 times 3 means I scale 2 by 3. I scale it to 3 means another 2 and another 2. I go all the way up to here. That's how I get my answer 6. So this is equal to 6. Okay, so it's a scaling and a rotation. I mean, it gets scaled up if you're multiplying by a whole number, or scaled down if you're multiplying by a fraction. And the positive negative thing would rotate you. So if you're doing, actually I want to, let's take this. If you want to do 3 times 3, what you would do is, right? You start with, I should have drawn all that with black. You start with 1, you put a 1 here, and you think, okay, I don't have to rotate. I just go to 3, and then I scale 3 times, I get to 9. I get to 9, right? If I want to do 3 times minus 3, I'm taking the same number here, because I'm thinking about multiplying the same number twice. That's what finding the square root is, to find which number multiplied by itself gives that number. So I'm just thinking, I'm just playing with this, okay, with you. If you have minus 3 times minus 3, let's see, it's 9 again. Let's see how that happens from this model that I just showed you. So you have 0, 1, 2, 3, and all that. 1, 2, 3, and so you start with 1. You start with 1, and then when you come to the negative sign, that means you have to turn. This has to turn, so it will come here. And times 3 means in that direction you will go to 3, so that's negative 3. And then when you come to this 3, you would turn again another 180. this turn is a clockwise in the same direction as blue. Say it's a clockwise turn. So when you get to this minus, your arrow would turn again by 180. So you would end up at the 3 here. And then this 3 would scale your arrow 3 times and would end up again at 9. This is how 3 times 3 is 9 and minus 3 times minus 3 is 9. If you think of multiplication as as a rotation, a scaled rotation, you have to rotate every time when you get a, depending on if it's positive or negative, and by that number you scale. You enlarge, magnify or reduce. Your arrow gets enlarged or reduced. Now, think of, so this answer is 9. This answer is also 9. Let's reverse this. If I want to think of what number should I be multiplying to get minus 9, so similar to minus 1. If you want, when you want to think of square root of minus 1, I can take any negative number for that matter, right? I mean, this is about square roots of all negative numbers. They are all non-existent. They're not on this line. They're not there. But let's think about it. 1 times some number. If I want it to be equal to minus 9, I'm just trying to show you how they came up with this genius way of placement of these numbers. Okay, so you have 0. I'm just showing you 0. All these are there. These are there. So you start with 1. That's your 1, right? And if this is a now you have to end up at no, okay, wait, shall I extend this? You have to end up at minus 9, right? Ane, shall I redraw this a little bit? Wait, oops, no. Give me a moment. Give me a moment. I'm trying to think of this. Here's my number line. Here's 0. Here are the other numbers. Here are the negative numbers. If I start with this, now I want all of you to think like mathematicians. That's 1. I start with 1. And now multiplication is what? It's a, I mean, we can do this if it is easier for you. Shall we think about negative 1? Yeah, let's think about negative 1. What number times what number? 1 times what number gives you negative 1? Okay.
3 times minus 3.
3 times minus 3. These two numbers have to be the same. Now we are thinking of.
It's minus 9.
Think of that.
Okay.
We got to think of that. This number has to be the same. It's a square root. Square root of a number means you get it.
Keep going and
wait. No. If you get confused a little bit, stop me. And
okay, Miss, then can you tell minus the root minus 9 part again?
Yeah, sure. Okay. Why I took that was because of this. Now, Malik, if you want to think of square root of say 4, we are thinking of square root of a number here. Now you already know what square root of 4 is, but if for a beginner who's learning this, how would we teach him? We would tell him square root of 4 means you have to think. Square root of 4 means you have to think of a number when multiplied by itself, same number. That gives you 4. That's the meaning of square root of 4. No? Some number times the same number must equal 4. What is that number? That number is called the square root of 4. So what do you call it? Candidates are there. 2 and minus 2. 2 fits in here. 2 times 2 fit in. Minus 2 times minus 2 fit in. That's why the square root of 4 is 2 and minus 2. Right? So similarly, now we are trying to find square root of a negative number. So I took -9 as an example. That's why if I want to think of what this is, what is the square root of -9 is, that means I have to come up with a number, one number, when multiplied by itself should give me -9.
The same way you did to root 4, but then you have to change sign. So it has to be plus or minus, like +3
Yeah, same. It
multiplied
should
by
be same
minus.
sign. That's right. Like,
Or -3
you can't have two
multiplied
numbers here. It can't be 3 and -3. That's not the square root then.
Yeah.
The very definition of square root means a number multiplied by itself. Same number. Should give that number now.
Yeah.
Right? Okay. So what has to come in these boxes have to be the same number. What is that number? That's what I'm thinking. What is that single number that I can multiply by itself to end up with -9 or -1? Let's think of -1. Okay.
Miss,
Now,
in the sense the sign should be the same too.
of course, identical. Same thing. But if you are telling me this is the number, then you multiply by the same thing. If it is 3, 3. If it is -3, -3. -3 times -3 then. It can't be 3 and -3. They are two different numbers. The number that you put here, it's a point on this line. Same point, same guy. Clear? Mali?
Yeah, now I'm figuring out how to get the -9.
Okay. Now, I want you to think of this one. Let's think of this one, not -9. Let's think of -1. We are trying to think what is the square root of -9. We are quite convinced that that number is not on this line, but just let's try to think about it, where it could be. So when we want to think about square root of -1, we have to think of a number that 1 times that number times that same number should give us -1. So geometrically, like visually, what needs to happen is I start with 1, that is this one, right? I start with a vector 1, and I have to do, these two numbers are the same. So now you remember, if the two numbers are two positive numbers, that means I would rotate 360, I would rotate another 360. So I would be facing the same direction. If the two numbers were negative, it's the same number. So if it was negative, with the first number, I would turn, I'm standing that way at 1. If this was negative, with the first negative multiplication, I would turn 180, and with the next one, I would turn another 180. That's why I again end up in the positive direction. That is why when I multiply when I multiply 1 times 1 is 1, and also -1 times -1 is 1. Right? But can you think of, I have to end up facing here. My answer is -1. My answer is -1. So I have to make 2 similar rotations. In this, what are the 2 rotations? You start facing that way at 1. You turn 180. You turn once 360 with this. You turn another 360 with this. So you end up facing in the same direction and pointing to 1. So correct. So it's 1. -1 times -1 means, how do you get that? -1 times -1. You start with 1, and when you say times -1, you turn this way, this is 0, and with this you turn another 180. I'm sorry, and then you are back facing in the positive direction. But for you to start facing at 1, and after multiplying by the same number twice, for you to end up facing in the other direction, where must be your number? What kind of a rotation? It has to be the same rotation twice. After two similar rotations, you have to end up here. Where should you stop in that middle? After multiplying by
minus 9 times root minus 9. Is that the answer?
where is it? How should you turn? How much should you turn? With the multiplication of each of these numbers. Now we are trying to locate where this number is. Where are you? Okay, if you're here in this world, you are not on this line. We know that, we are sure of that. But then where are you? Like, to locate where that guy is.
So root minus 9 would be
We are
minus
thinking of
3,
one.
right?
Do we want to go to this one? Minus 9?
Okay, so then for minus 1, the same thing, right? It's root minus 1 is still.
Yeah, so this number, yeah,
it wouldn't make
I
sense.
can write it. This is square root of minus 1 square. But can you show me in this diagram? So how do you turn? Like, you start at 1, that is this number.
Yeah,
Then
according to the
times,
diagram, it doesn't work.
can you think out of the box?
You've already written out of the box too.
What's that?
You've already written out of the box, so I'm supposed to think again.
I have written out of the box.
Like literally in the diagram.
No, I haven't shown you that.
Miss.
Yes, Nathan. Mihil,
So
Nathan.
Nathan.
Yes, Nathan.
This is now we have to find minus 1, right?
We have to find where square root of minus 1 is. If that number is there somewhere, where is it? And multiplying by that.
I can't multiply by its own number. So that if it's minus 1 into minus into 1.
1. Now, two things have to happen. The length of my line can't change because I start at 1. And then after this multiplication, I multiply by a square root of negative 1 and again by a square root of negative 1. So the rotation has to be similar and my length of the line can't change either because I end up here at minus 1. The length of my arrow is the same. The size of my number is the same. The modulus is the same. I mean, so think of how you should rotate this arrow. There has to be 2 rotations involved because you're multiplying twice by that number. There are 2 of those numbers. You start here and you end up here. How should that rotation go? How should it happen? Just think like you have this. I don't want to say it. I want you to tell me. You start with this. This is your start. That is your end. And you have to rotate on this plane. That's the other one, right? You're on this plane. You're rotating on this plane. I wish I can I rotate stuff in this? Let's draw that. And then I can, like that. Okay, let me bring it here. What is happening? Now that I don't like, it suddenly just gets zoomed. Where is my arrow? Shall I just redraw something? Have I messed up this diagram? No, that's actually another thing. For you to think clearly, your diagrams have to be clear. Then you have clarity in your thinking. And so on. I'm thinking, I want to find what is. That means I want to come up with a number. I want to come up. I want to create it. I have to create a number. I have to come up with a number. Such that if that number is this, I mean that is square root of -1 only, but it's not. Let's call it square root of -1. But where is it? I have to find that number such that 1 times, seriously. I'm lost. Where am I? 1 times that number times, no, I don't want that to happen. I don't want that to happen. Times that number again, I don't want that to happen, must equal -1. That means on my line, I start with my arrow. Yeah. And I have to end up, I have to end up my answer. I have to end up here. This is the one I start with, this, right? That is this one. And this is my answer. Or let me completely draw it this way. So I started with that. I have to end up with this. So I have shown it on the line. How should I be rotating? Because with the multiplication of each of these numbers, this is the same number. This is the same number. Who's here? This guy. But where is he? Is there a way that I can rotate on this plane? So that I have to end up. Sorry, that got messed up. Okay. Let me give you a few minutes. Are you thinking? I am thinking. Think like this. You want to create this number. You want to find a place for this number in this picture. It's not yet been created. So it's not a number on this line. This number, this number, this number we are sure of that. It's not on the real line. It's not on the. But I'm trying to create a spot for him. I'm going to create a spot for him. Where can I place him? I'm going to place him somewhere. It's just the same. Can you go back and think of how we had, when we had 0, 1, 2, 3. The number line like that. When we wanted to create negative numbers, naturally it comes, oh, let's extend this line in the other direction. Then we will have all the negative numbers on the other side of that line. Because before that, the line had a beginning, 0. It began there. There was nothing before that. But how did we accommodate negative numbers? We gave them a place on this line. You can sit here. It's like that. And that would fit that would not disturb our picture. It nicely fits into our picture. So we gave them a place by extending, we created it. Similarly, in this picture, now you have the whole line. So you have to understand that. And if these new guys can't be on, they're not on this line, and then we have to like think out of the box to see where could I place them then? And I'm trying to, the reason why I give this scenario to you, this multiplication thing, is for you to think how I can bring in something new to be consistent with the rest of this is how I do multiplication. So I want to place this new guy. Here's my new guy. I'm trying to give him a place in this picture. But my multiplication, how I have been doing multiplication, that has to, I have to, how does it? That I can't violate rules of multiplication. If I bring this guy in, the multiplication has to happen the same way. But now, what is my requirement? 1 times this new guy times the same new guy must equal -1. This is a number I know. This is a number I know. So I have shown you the starting number and the ending number. I am trying to place this guy. I have to think of, I start with this red arrow. I have to do a certain rotation, keeping the length the same, because when I end, I end up with the same length. I have to do a rotation. I have to repeat the same rotation when I multiply by the other one. And I end up here. Can you tell me, when I have multiplied by just one of these numbers, where I should end? In the middle. In the middle means I like after 1 times this number, where should I be? For me to do another similar rotation and to end up here. I'm rotating around 0. And I'm rotating clockwise.
Is it
because this,
where we
the
can't
sign of this is positive. No, the sign of this number is positive. Huh?
Is it
Malik?
somewhere we can't see?
Yeah.
Miss, can you check our discussion? We had a little discussion in the chat group, chat box. And
Yeah,
can you tell whether...
in this, I can't see. Yeah, wait. Oh. Oh, I'm
Can
so
you
sorry.
tell whether...
Wait. Let me read all this. Let me read all this. Oh my God, you have been talking to me now here. I didn't see any of this. Because in that whiteboard, the chat box, when I press, it doesn't come. I have to press participants to see the chat. Wait, now, from where did I have lost so many of your... I'm so sorry. Can you give me a moment? I want to read all of this. From where did it start? Flock of sheep, Stone Age. Yes, you have given me answers to those also. I did not see any of this. Mind-blowing, infinite. Oh my God. I wish I had this feedback while I didn't see any of this. So I felt like I was just talking to blank.
I don't know. It's just now math sounds different to me.
What is that?
Math sounds different to me now.
Oh my God, I'm so happy to hear that. I'm glad I'm recording this. Infinitely many irrational, you're saying, you brought what? Wait. I don't know how to go up in this. God brought that number, yes. I was talking about, I will. Wow, I feel like I'm seeing maths with a new lens. That's crazy. Who else is mind blown by this?
Just go down, Miss. Yeah.
Miss 90, 90 left and 90 left. Oh, Hatfi. Yeah, sorry. Malik, and please put your messages to everyone. Now, Hatfi has privately messaged to me how to rotate. Okay, Miss, I can't do with the clues anymore. Please give the answer. Oh my God, I didn't see that. Let's imagine something exists. Netni says, Hatfi, Malik, I think it's a 90 left and 90 left. Does that make sense? Sort of. because it's 180. Yeah, I get what you're saying. Just have trouble processing it through. Okay, so what's 90 left? I got how you got it through the number line. I want to apply it numerically. Yeah, I also don't see a connection numerically. Okay. Let me go back. You have already, that is exactly what it is. This is so difficult to do because we are stuck on this line. We are stuck in one dimension.
That's what I was trying to say. So if like we want to get -1, should we like go out of the line and
Of
then just
course,
get
and
into
that is
some
so,
obscure
yes,
point and then
and
drop back?
yes, can you see how hard it is for us to do? What do you mean by going out of the line? Because we think we have to be on, we think now numbers are on this line, so we are bounded, we are like that, we say bed bound, we are stuck in the line.
So Miss, I'm
you have to
guessing
break
like
free. Yeah, you have to come onto 2 dimension.
so Miss, I'm guessing the 90 left is like coming out
Outside
of the line
let
to
me,
that
yes.
imaginary point and then falling back.
Exactly. So what they did was the way we think of multiplication would nicely, I can extend, I'm extending the story. So if this is how multiplication is being done, and now I have to come up with 1 times a certain dot somewhere in this diagram where this number should be, The moment I draw on this, that chat box disappears. That's what happens. So I don't know how to do that. Even now I took it back, but now when I write on the pad again, the chat box disappears. So it would be great if you can talk, people. Okay, anyway, I'll try to time take it. Okay. So I'm trying to place a point for this now. So as some of you have rightly said, what I can do is I can think of it as, now I have to rotate this arrow now. I have to rotate this arrow. If I was multiplying by a positive number, I would rotate it by 360. If I'm multiplying by a negative number, I would rotate it by 180. My rotation is always clockwise. If I have to multiply by this new number, which is a square root of a -1. What I can do is, let's think of it as rotating, come on, by 90 degrees. And then I go here. And that is this guy is. I mean, that's why I place him there.
Okay. Now I understand. Now I get why they have the imaginary and real axis.
That's right.
Okay.
So if I place him here, and then place him here means multiplying by, now you know that this was later conveniently we started to call it I. Square root of -1 was called I. So just like multiplying by, and then okay, similar, let's see how this works. So when I multiply by this, it is equivalent to a rotation of clockwise 90 degrees. So if I do 2 of those, I end up at -1. Correct. So 1 times square root of -1 means rotate 90 degrees. Again times by square root of -1, rotate another 90 degrees clockwise, and I end up at where I want to end up at. So that means this, your real number line, where all your real numbers lived, that's fine. But these new numbers, if you want to give them a place in your picture, where should they live now? Because you have to be thinking of, now I know you have learned this already. You have to have asked the question, why do you place them on a perpendicular axis? Why do you say I is here? Why couldn't it have been, I mean, who came up with that? It was created to match our existing way of thinking. So when you say it's here, and when you say, I don't know what's happening. So multiplying, now I will summarize this again. Multiplying by a positive number, let me write it, no, not symbols. multiplying by a positive number. Say it's positive number means rotate clockwise 360. Multiplying by a negative number is rotating clockwise 180. Multiplying by this guy, the new guy, square root of -1, then we will see how all square root of other numbers, how that all come into this, would be rotating 90 degrees clockwise. And that's fine. I mean, that completes the picture. So with this, so what just happened is this. Oh, so we just created a whole new axis for the number line. So we can take 90 degrees motion as a thing. And that axis is called imagine. That's right. So real numbers are on this, and these new numbers are on this. All the square root of negative numbers could be thought of as living on this line. And then you have to be asking another question. Wait till I read your. I really wish Zoom had GIFs so that I can explain how I'm feeling. I still don't. You still don't understand? It's fine, Nathan. It's fine. It's fine. Just give yourself some time, some more time. And maybe I was a bit too fast, and maybe I was not very clear, because I get very excited myself, and the no, wait. Don't think like that. Wait, Nathan. Let me now. Just keep listening. There would come a point it will click to you as well. Okay. Wait. Don't cry. Wait. What was I saying? I was saying, so with this, you have to ask, okay, all the real numbers are on this line. And now we just extended this is very difficult to do. Numbers no longer live on a line. Numbers live on a plane. There is a whole plane of numbers.
So if we want to reach completely to the negative side of the number line,
yeah,
we have to go through it. The imaginary axis is like a bypass route.
Yeah, that's correct.
Okay.
If you're multiplying by a negative number is bypass, means you're rotating completely 180. Now remember, these rotations are done on the plane. Okay, you're rotating on the plane, like you're not coming off of this is not 3 dimension, this is 2 dimension. So this now numbers exist on a whole plane. And now you have to be thinking, so this, what is this I?
I is root -1, right?
I is, now this is a symbol that we have taken for convenience. This is square root of -1. Okay, square root of -1. If we can place that single number, all the other rest of the negative square root of negative, all other square roots of negative numbers, no, square roots of all other negative numbers could be, they have a place on the same line. I will explain how that happens. So I mean, if you want to think of square root of, now put any negative number. Now this is -1, square root of -2, square root of -3, square root of -4 is what 2i is, because square root of negative, I'm sorry, I think when I get excited, I like say things fast and write things fast, and I write things messy also. Nathan, I'm sorry, I'm pretty sure it's my fault, because I'm like, sometimes I speed up saying things and then you miss to catch that.
I think it could be the the lesson itself is kind of complicated.
It's complicated as well. Yeah, true.
Yeah,
because
so
it's,
that's there too.
You have to you have to really come out of a box.
You have to, like, I don't know, it's like looking at maths at a whole new angle.
That's
whole
right.
New way.
It's whole new, yes. So Nathan, just be patient, just keep listening. What I said was, what did I write? What was I going to say? So think of Let me go to a new place. Think of you want to do negative square root of negative 4. Square root of any negative number could be written in terms of square root of negative 1. Because now look at this one. I can write this as, I hope you remember surds. This is actually a surd, square roots. I can write this as negative 1 times 4. Right? Square root of negative 4 can be written as square root of negative 4 can be written as negative 1 times 4. So this is fine. And then I can simplify this as, you know, I can separate this out as this. This we learned when we learned surds in the beginning. And then this is what we called I, and this is 2. This is plus or minus 2. So this gives rise to 2i or negative 2i. So where is negative? Oops. Where is negative? This is 2i. So 2i means square. This is equivalent to this one. And you have negative I also. You have negative 2i. You have negative 3i. So this goes in multiples of I. And what is this I? I is the one who has a length of 1. His length is 1. His size is 1. The distance from 0 to this number is 1 magnitude. The same length you have here. You understand? The size of I now. This I is a new number. What is I? Square root of negative 1. And where is it on the number line? It's not on the number line. It's on this plane. It's on a vertical line. We created it. We brought a new line of numbers. And all the square root of negative numbers could be put on this line. Now, I am too excited. I want to go into the next question. Are you already asking? Then are there numbers here in these spaces? No, now all the real numbers are on this line. All the real. Now don't mix this up with the coordinate. This looks like a coordinate XY axis. No, it's not the coordinate XY axis. These are your numbers. This is your number world, the world of numbers. Okay. Let me look at your, yeah, I'm just trying to see whether you're saying anything. Right. Okay. So so I said all the real numbers are on this line. Then all the square root of negative numbers, square root of negative 10, square root of negative 3, square root of negative 139, square root of negative. Think of all those numbers. They are all on this line. They have a place on this line. Okay. Then what about now? With the introduction of this new line of numbers that is living perpendicular and passing through 0 of the real axis, with this, when we brought this into our picture, it created a whole plane. So now a plane means there are spots here as well. Spots for a number to live. Are there numbers here as well? Is there a number here? Is there a number here? Here? Yes.
Yes.
This gives rise to a whole new family of numbers.
Universe.
And they are the whole universe. And all those numbers all together is what are called complex numbers. Just like we had real numbers. Now the thing is this choice of word for this new type of numbers, to call them complex is a bad choice. And to call these, what did we call these numbers? Imaginary numbers. We shouldn't have called them imaginary numbers, because that very word mentally obstructs your thinking. Like you tend to think, then they're not there. It's just like thinking, do you ever think that negative numbers are actually not there? No, they are there. They are very real to you, right? All these numbers are very real. But unfortunately, we are stuck with the word real. We call these real, we call these real, and we call these imaginary. They are all very real numbers. I mean, now when I say real, only these are real in the word real, but
they're
they
like
are all
imaginary numbers which have this real part to them.
Existence.
Yeah.
They exist basically. Okay. But they were called, because originally when they were found, because they were first called, I think, impossible numbers or something, and then turned to be called imaginary. We took on that that word, and then oops, and then just think of, okay, now this is like, Nathan, vanilla ice cream and chocolate ice cream. So it's like the real numbers are like vanilla ice cream, this pure vanilla.
Okay.
Imaginary numbers. Now, what do I call as imaginary numbers? It's just a name. Okay, don't think of the meaning of the word imaginary. It's just a name. It's like sometimes we call there are people. There are names of people, but that name doesn't reflect the actual nature of the, like, for example, there are jokes for this. We say Dhanavati. I don't know, in Sinhala only I have this example. People say there is Dhanavati, but Dhanavati is poor. Her name is Dhanavati. Dhanavati means rich, but she's poor. Just like that. Now these numbers are called imaginary, but they're not imaginary. They are very real to us. So anyway, they are called imaginary, right? And then I forgot what I was going to say. Like, so many thoughts are coming into my mind, so I don't know what to say first. And it's all, and again, my thumbnail is blinking. Why are you blinking?
The thumbnail answers.
Maybe it's responding to the lesson, maybe. Don't blink. Imaginary. These are called imaginary numbers, right? So what I was going to say was vanilla and chocolate, Nathan. Okay, so all the real numbers are just on this line, and all the imaginary numbers are just on this line. So it's like all the vanilla is here, the chocolate is here. Like they're two different, they're different, right? Then who's here? The numbers that live like in between, in the middle of on this plane, not on the two lines, but anywhere else, they are a little bit of vanilla, a little bit of chocolate, because they have components of both. If you think of a point right here, this, let me draw in a different color, but like a point here, a number, right? Number sitting, number living there. It has kind of a component of the real, it has a real flavor, and it also has a imaginary flavor to it.
So it's like the taste we need is vanilla, but then we put a little bit of chocolate to it.
It's like it's a mix of vanilla and chocolate.
But you still have the vanilla in it. So
it has both vanilla and chocolate in it.
Yeah.
It has a vanilla flavor to it, and it has a chocolate. It's like a mix of the two. So like if you think of any number on this line, it's pure real. It's pure vanilla. Think of a number on this line, it's pure imaginary. It has no real part to it. It has no chocolate whatsoever to it. But for any other number somewhere here, it has both components, both parts, both flavors. Because when you are here, you have a component of the imaginary part. You have an imaginary part to it, and you have a real part to it. And in general, now we are going to generalize the whole thing. Okay, now here's the concluding. Now I'm going to draw the final my understanding of numbers is, here it is now. So what are the known numbers to me now? My numbers, they live on a plane. Now it's no longer real number line. All this time we were saying real number line, real number line, real number line. Our numbers were living on a line. No, there are more numbers that are out there. They all live on a plane. So,
wow.
Nathan?
So which means if they all live on a plane.
And just let you
Miss, I'll send you a picture of what I was actually trying to think of, but
on WhatsApp?
I'll send you a picture. Yeah, on your, I'll send a private message.
WhatsApp?
Yeah, WhatsApp. So basically, give me a second, I will.
I don't have. I haven't
No,
received
no,
it.
I didn't send it yet. I'll send
Yeah,
it
right. Okay.
by
So with the amount of things I have spoken so far, I will leave you, giving you your break, and let your mind travel in all these directions and think about this, and more questions might come up, and we'll just then put everything together, and then after the break only we will formalize everything that we just discussed. Like we will get into the formalities of it, and now this is how we write it, this is how we operate with it and all that. But what I hope to give you with this, I spend like that's close to 2 hours. I hope what I was able to give you, what I hope to give you was the picture and the story and the nature of mathematics, how it's all done. Everything in math is, that's how it is done. And this is a nice topic to show you that, to give you a glimpse of that. This is how all math is created. And it's just that we learn it in a way, in a very dry way. It's there, and here it is, you learn it. You just learn things, right? But the creation is